Log on, tune in, find out. Another good idea from Cambridge.
It is my pleasure to introduce the last speaker for this afternoon, David Hernandez from CNRS ENS Paris, who will speak about Langlands duality for representations of quantum groups.
Okay, thank you very much. Thank you very much for this opportunity to talk about this work. So the title is Langlands duality for representations of quantum groups. Okay, so this is a joint work with Edward Frankel. And we have two papers on the archive about this, so I just give the references. Okay, so the aim of this talk is to present some Langlands duality in the context of representation theory, but internal to the representation theory. So to explain this, let me start with the motivations, which comes from a well-established context of Langlands duality. So motivation. So the motivation comes from the Langlands correspondence, which appears in many topics in mathematics. So the origins is in number theory, and there are also geometric Langlands in complex algebraic geometry. And there are relations to physics. And in all these situations, so we have some correspondence between some objects which are attached to some, let's say, some Lie group, G, so attached to G. And on the other side, some objects attached to the Langlands dual group. Okay. So in number theory, this is, for example, the Galois side. And here we have some automorphic side. And so we have some duality or some correspondence between some objects. But so in number theory or in Langlands geometric, for example, objects on both sides are not of the same nature. Okay, so these are not of the same nature. Okay. So this is a general motivation for this. So in Langlands geometric, so there is something which is very important, which is, so there are some geometric objects which are hoppers, so attached to some Lie group, G. And so there are some, if we look at the functions on this, so it is well known that it's related to some W algebras corresponding to the Langlands dual Lie algebra. Okay. So I mean classical W algebras. Okay. So now, in fact, it's there is a relation between some quantum version, so quantum W algebras, and the representation theory of quantum affine algebras. So in fact, representation of UQ of G hat So this is the Grothendieck ring of finite dimensional representation of this quantum affine algebra. Okay, so Grothendieck ring of finite dimensional representation of UQ of G. Okay, so this is this relation is due to Frenkel-Reshetikhin. And in fact, they ask the following question. So if we look at this, okay, so we have this important W algebra and their quantum version, which are related to this object, this geometry. And then, what? Here? Here it's a quantum deformation. Yeah. And so we can ask the following question. So is there some relations between the representation theory of this quantum affine algebra and the representation theory of the dual affine algebra? So here it is, so if we suppose that this is, for example, non-simplaced affine Lie algebra, we have some twisted affine Lie algebra here. So this is a question of Frenkel and Reshetikhin, 96. Okay, so in some sense, so it is motivated by this story, but the picture is a bit different because here we have objects of the same nature, because we have some representation of quantum affine algebras. Okay, and so in fact, to try to understand, to have some answer to this question, they introduce some double deform W algebras, WQT, to interpolate, in some sense, the representation theories. Okay, so this is, in fact, the starting point for this work. And in fact, to start with, we can ask a more naive question. Okay, so if maybe it's possible to relate this representation theory, maybe it's also possible to do it at the level of quantum group of finite type, okay, without finite. So other, let's say, naive question. So let's take UQ of G. So now G is just a finite dimensional complex Lie algebra. And we would like to relate the representation theory of this to the representation theory of the dual. And some question which is much more elementary: is it possible to do it at the level of Lie algebra? Okay. So what I would like to explain today is that we have some positive answers for these three questions. And this will be the three parts of my talk. So the first part will be very elementary representation theory, okay, related to finite dimensional representation of these Lie algebras. But so as far as we know, we do not know reference where the observation and result that I will give have been at least considered in the context of this Langlands duality. But so in the first part, we will look at some, so the representation of G. And I will give some precise connection between these two representation theories. So in the second part, so I will answer this, at least give some indication to study these connections. So, and to do it, we will discuss new algebras that we have introduced that we call interpolating quantum group. So which is an algebra which depends on two parameters. And depending on the specialization of the parameters, it will give one quantum group or the Langlands dual quantum group. Okay, and the third part, in fact, will be, which is the closest to the original motivation to the Langlands geometric, is related to the representation theory of this quantum affine algebra, but the finite dimensional representation, which in fact had much more complicated to study than the finite dimensional representation of quantum groups, as was discussed, for example, yesterday in Shari's talk. So here we will see for finite dimensional representation of quantum affine algebra. So I do not say that the picture is totally complete now, but I will give some explain results and conjecture in the three parts. Okay, so I should. So as I said, the first part will be the most elementary part for this. So we start with G, which is finite dimensional simple in algebra over C. Okay, and we take the Cartan matrix, and we have the lacing numbers. So R1, Rn, where n is the rank of G, and we consider the lacing number of G, which is just the max of the Ri. Okay, and so it's the Langlands dual algebra, so G dual, or just the length of the root. Yes. So the Langlands dual Lie algebra is the Lie algebra defined with a transposed Cartan matrix. So C transpose matrix to C, and then the R are transformed so to some Ri dual, which is R plus 1 minus Ri. Okay, so this is the definition. Okay, so for example, if G is simply laced, then it is unchanged, the same. And if we have, for example, B2, then we get C2. And if we take B1, which is the limit of Bn, so it's kind of SL2, but we suppose that R is equal to 2, then we get C1. So it seems to be a trivial example here, but this will be important for us, for our picture. Okay, so this is just SL2, the two are SL2, except that R is in one side R is equal to 1, Ri is equal to 1, and the other side it is equal to 2.
So will you be attaching quantum groups actually to algebraic groups rather than real algebras? Meaning including the center, taking into account the center?
Or we will just do it at the level of the algebra. Is it your question?
Yeah.
Because of this picture, it seems that they use algebraic groups. Right?
Yeah, it seems that you're dealing with groups. That is SL2 and SO3. Is that correct? Quantum SL2 and quantum SO3.
Yes.
So you actually will be quantizing groups.
In this sense, yes. Okay, so So let's look at some examples. Okay, so very elementary example, I take a representation of SL2. So I give examples to explain what we will do, in fact, in the general case. Okay, so for B1. Okay, so we know that I take L to n, which is a representation of SL2 of dimension 2n plus 1. Okay, so we know that the character is 2n, y2n, y2n minus 2 plus y minus 2n. Okay, so it is a symmetric polynomial. And then, so I think it is the most elementary example of Langlands duality in representation theory. What we can do is to decompose the symmetric polynomial into symmetric polynomial in the following sense. So we have y to n, and then instead of taking this one, we take the next one. Okay, so 2n minus 4 until plus minus 2n. Okay, so it's kind of the half of this polynomial, and then we have other terms. Okay, and so here we have a symmetric polynomial in the variable y to the 2, and here y to the 4. And so in this picture, it just means that we have multiplied by 2 the length of the root. And when we do this, we can decompose the character of this representation as a sum of two characters of the representation. Okay? So, of course, this example is very elementary. So, let's look at an example which is.
So I'm a little confused. So you took r equals 2, but in this setting, I don't see why can't you take r to be any positive number?
You could, yes.
But then the separation of taking dual is not involutive.
No, it's not. No,
So
that's the point. This duality that we study is not involutive.
Ah, okay.
What do you mean by 2n plus 1 underline?
What do I mean by what?
No, in the next slide.
This is 2n minus 4.
On the left.
To the left, to the left.
Oh, I just said that this is a representation of dimension 2n plus 1. Oh, let's forget. So the highest weight is 2n. That's what I
So maybe again in the beginning. So what are these R1 through Rn? So they are lengths of square lengths of roots.
Let's say if you take the diagonal matrix given by the Ri, then DC is symmetric.
But, are they integers?
Yes, prime to each other. The standard.
But otherwise, their normalization is not. You don't require any normalization.
No.
You can multiply them by any positive.
Yes.
Number. Okay.
Yes. Just to have a non-trivial example in SL2, but now I go to usual B2. Okay, and I look at a 5-dimensional fundamental representation. Okay, and so the character is y1 plus y2 squared, 1y minus 1. So we have a 1 plus y1, y2 minus 2 plus y1 minus 1. Okay, so this is the character of a fundamental 5-dimensional representation. And now you see also that you can decompose it in two parts. And here you have a character of a 4-dimensional fundamental representation of C2. And here some trivial representation of C2. Okay? So now let's formulate this in the general situation. So we take a G arbitrary simple finite dimensional Lie algebra. And so let's take lambda, highest weight, which is in fact in a P prime. So P prime is some sublattice of P, which is defined in the following way. It is a sum for I in 1n of Z, okay, R minus Ri plus 1, lambda I. Okay, so this is a fundamental weight, and we restrict ourselves to the case where lambda, the coordinates are multiple of this. Okay? And so we have key of L of lambda, which is a character of this simple finite dimensional representation. So it is an element of Z of T. And we take the projection to on P prime. Okay, so we project projection.
I'm sorry, it's again about this formula.
Which
for
one?
dual RIs. It
Okay.
doesn't seem that if you normalization of R is not fixed, it doesn't seem that if Ri is a symmetrizing vector for C,
No.
then RIL will be symmetrizing for C.
So what makes you confused is this B1. So let's forget about this B1, okay, which is just a kind of pathological example. And that let's take a Lie algebra, and if the algebra is simplized, R is equal to 1, and if it's type B or C, F4, it's 2, and G2 is 3.
Okay.
I just said that for B1, you have some B1 notion of B1. In this case, you have two in fact. But it's just a kind of sub-Lie algebra of B2. That's one.
Okay.
Okay, so I have to go a bit faster. So let's take, so we get T prime of L of lambda. Okay, and then now we will do some identification of the weights of the Lie algebra G to some fundamental weights of the dual Lie algebra, as we did here. So the identification is the following. So R plus 1 minus Ri lambda I is identified with the dual fundamental weight if Ri is equal to 1. And it is identified, so lambda I is identified to the Langlands dual fundamental weights if Ri is not equal to 1. Okay, and we do this, and so we get key second of L of lambda, which is now some element corresponding to the dual weight. So this is exactly the transformation that we do here. So here, in this case, the projection, nothing is cancelled. And then this is identified with a fundamental weight for the dual Lie algebra. And Y1 also is not changed. And so now I can state the theorem. So theorem 1. So the first point is that what we get is a character of a virtual representation. So this is in the character ring of the dual character map. Okay. The second point is that this character contains the character of the finite dimensional representation whose highest weight is the dual character. So it's bigger than the character of the Langlands dual representation. Okay, so this is exactly the situation that we have here. So we have this big character, and this character is in the character ring, and the first part, the first component, is the character of a Langlands dual representation. And the highest weight here is a weight which is obtained by this one, from this one by the transformation that I explained.
In what sense it's greater or equal? You said it's
So
a
this-
virtual representation.
So this inequality is just a natural inequality on polynomials. So you have two polynomials, and one is bigger than the other one if and only if all coefficients, we have the equality for all coefficients. Okay.
Yeah, but you said it was a virtual representation.
No,
So-
so now I come to the
strongest
analysis.
side.
Yes,
But if,
a priori, so we know that the coefficients are positive.
That's why I was asking, because initially you said it was virtual.
Yes, so you have a character, you have the expression, and the coefficients of the weights are obtained from the coefficients of the weights from the first character. So all of them are positive. But now it is a sum of character of a representation for the Langlands dual representation. So we may have some negative coefficients.
They the negative cancel out as well. I mean, what's left is after you remove this piece, it's still positive coefficient.
Well, so the point is that I will give now a result that in fact it is a real representation. So this answers the question. So we have this conjecture. That in fact this is a character of a real representation. And so we had checked this conjecture for B2, and it was proved very recently by Kevin McGarty that this is true.
I suppose the first step is just some property of wild group invariant.
Yeah, no, it's not difficult to prove. This first step is just to check.
Well, we have to check that it is over Q, yes, but this is over Z. It's a statement over Z. Coefficients are easy.
The coefficients are integers, and to prove that this is a character, it's not a difficult theorem. You just take, as you said, the dual group, and you check the invariance. But then you have to check that it's compatible with all this transformation.
So I don't understand the second statement. Isn't
Okay.
the second statement saying what greater than or equal means that it is that character plus some other positive sum of characters?
So we have the first character plus some terms with coefficients on weights which are positive.
Okay, I understand.
Okay.
But so greater or equal means on weight,
Exactly.
not on characters.
This is what I said.
Okay.
It's a polynomials.
In this C2 example, if you start not from B2 but from C2, you start from a four-dimensional representation.
It's not involutive. Maybe it's your question.
Okay. It goes.
Okay, so I said this is proved. So which is a very nice result by McGarty. And 2009. So which gives encouragement to continue to study this. So now I'll go to the second part.
So
And
for
this is purely combinatorial, just sort of some McDonald in a product or something like that.
What is purely combinatorial?
This statement is a proof.
No, the proof of the second point here involves some crystals.
Oh.
So this duality, a priori, you can ask the question at the level of crystals, if you have the same, and it does not hold. We have a counter example. But so the first statement, in fact, if you take the whole crystal, you can you can define operators corresponding to the Langlands duality algebra, and you have some connected components, and you can ask, is it a crystal of a representation of the duality algebra? So you have the main component is. And this is how we prove the statement. But other components are some G dual crystal, but not crystal of representations.
If you just computed the McDonald in a product on these characters, would you get such a result? I mean, that seems like the most obvious thing to do. You just compute you just try to compute the terms by calculating the McDonald in the product.
Oh yeah, we did not try, but
You
maybe
didn't.
we could. So as I explained in the intro, so this is just a classical type. What we are really interested in are the double deformations that I would like to explain now. But just I wanted to say, okay, this whole picture with this quantum affine algebra, we can look at the trace of this Langlands duality at this very elementary representation theory of Lie algebras. Just mine. I did not want to have 1/2 hour about it.
So for simplest case,
I'm very glad you are interested in this. Yes?
the simplest case is the identity map, right?
Yes. Except if you change the normalization, but okay. So let's go now to the second part, which is about this interpolating quantum groups. So what we want to do is to understand this duality from this original motivation of Frankel and Reshetkin with this double deformed W algebras. So what we did, we defined some. We define some algebra U, Q, T of G, okay, which depends on two parameters, and we proved the following. So if T is equal to 1, then the specialization of this algebra is UQ tilde of G. So tilde means that we did not use the Serre relation. So it is a quantum group without quantum Serre relation. But for what we want to do, it's not important because the finite dimensional representations are the same with or without Serre relations. Okay? And we do not put them because we have a proof that we cannot impose a Serre relation in our picture. Okay, but so and then if we take the specialization,
but presumably you have some extra relations.
What?
I mean, the algebra you start with is sort of finite GK dimension, so you should end up with something which also has.
I did not explain what it is yet. I have not said what it is. Okay, it is a double deformation of this enveloping algebra.
Does it have finite growth rate?
I don't know. I will give the definition in a few seconds.
So did you just say that if you don't impose the Serre relations on the finite dimensional representation?
Yes, if you take, it's true for a usual Lie theory. If you take semi-simple Lie algebra, the Serre relations are in the representation, but you don't need them. So Q now is equal to exponential 2IP to the R. So it is the root of unity. And then we get the Lie algebra of the Langlands dual. Okay, so let me give example of this. So I have no time to give the whole definition. So let's look at this B1 case. Okay, so we have this UQT on B1. Is some algebra. We have some generators. So one generator for the Cartan algebra for the first specialization, one for the other one. And the point is that for the other part, we have positive generator and a negative generator. Okay, so we have 4 generators. And so I have no time to write all relations. So we have some relations. And the point is that, so when you put t equal to 1, so you look at the subalgebra generated by the k, the x plus and the x minus, and you get uq of FL2. And for q equal to I, so you look at the k tilde, k plus to the square, x minus to the square, and then you get u T2 of FL2. So, okay, a priori, you may ask why is it interesting to have this situation. So now I will explain why we think it is interesting.
But in general, are you going to take the pairing between, this looks like the pairing between U plus and U minus?
Between the this algebra has no triangular decomposition.
No what?
Triangular decomposition. This one.
No, but I'm just saying that you could take the positive Borel, the negative Borel, and then you get a Hopf pairing between these two parts. And then normally what Drinfeld did is that he identified the top.
Yeah.
You haven't identified it.
No.
You've left the top. So in the general case, will you take the non-degenerate Hopf pairing, or will you?
This picture is not really compatible with the Hopf algebra structure because this is not a Hopf algebra. So we tried many things, and in fact we arrived to this algebra as the only thing which works. maybe there are some other ideas, but maybe if you have another idea, I am interested to know that. So I will explain maybe why this is how we get to this algebra. So let's take, I go back to this example for SL2. Okay, so let's be simple finite dimensional representation of UQ SL2. Okay, of highest weight 2n okay, lambda. So if you look at the matrix coefficient of the action of the quantum group, you get some quantum box MQ. So this is well known. And what we can do is we t-deform the action of the quantum group in the following elementary way. So we just replace MQ by MQ if M is odd, and MQT if M is even. Okay, so this is very simple. I take this finite dimensional representation of UQSL2, and I t-deform the action in a very elementary way. I change the quantum box, but not all of them. If M is odd, I just do not change, and if M is even, I change MQT. And the point is that when I do this, the relation between the generators of the quantum group do not depend on the representation. Okay? For all, it does not depend on n. And so I get an algebra, which is exactly how we get to this algebra. And the point is now, if I take this specialization at t equal to 1, obviously it is an action of UQSL2, because it's but if I put q equal to I get the action of the Langlands dual quantum group. And when I do this representation, which is simple as a representation of UQSL2, decompose in two simple representations according to the decomposition of the characters that I gave previously. Okay, so as I have not so many times, I would like to go to the third part, which I think is the most interesting from my point of view.
And is this used in the proof of the combinatorial theorem?
No.
But can one prove it also using this deformation?
Now, yes, if you have this deformation, you have a proof for this one. Okay, so now let's go to finite dimensional. Of this quantum affine algebra. Okay, so I don't know where if I can write. So there is a replacement for a usual character theory for finite dimensional representation of UQ of G hat, which are Q characters. So which are characters. So this is the Grothendieck of finite dimensional representation of this quantum affine algebra, and this Q character map gives polynomial, Laurent polynomial in some infinite. So Laurent polynomial with infinite number of variables, indexed by I, and some spectral parameter, etc. Okay, so this is Frankel-Reshettikin. Q character. Okay, so it is they prove that it is injective ring morphism. Okay, and so the way it is defined, it is some character theory which is adapted to the Drinfeld presentation of a quantum affine algebra. So in this Drinfeld presentation, there is a big commutative Cartan subalgebra, and the action of this algebra. So if you look at finite dimensional representation, the action is not diagonal, so it's not as good as the usual, in this sense, usual character theory. But as the action of this algebra is the operator commute, we have a decomposition in Jordan blocks. And this map encodes the decomposition in Jordan blocks. for this big family of operators. Okay. So in this 96 paper, they computed some Q character of fundamental representation and compared them with what we get for twisted quantum affine algebra. So let me give their example, which is really the motivation for this kind of relation between characters. So we start with a UQ of B2 affine. Okay, so this untwisted quantum affine algebra. And we look at a 5-dimensional fundamental representation. Okay. So the Q character is the following. So we have Y1. Okay. So instead of having variables of usual characters, we have variables with a spectral parameter here. Okay. So which is the following. So we have this, and we have some Y2Q to the 3, Y1 Q4 minus 1. So if you forget the spectral parameter, you see that you recover a usual character. So it's 5-dimensional, so there are 5 terms. Okay. So it is almost as a usual character, and if you forget the Q, you get a Y2 to the square. So if you have you remember the usual character, it is the same. So now, it can be compared to a 4-dimensional fundamental representation of the twisted quantum affine algebra, so which is Langlands dual to this, so which is U T D 3 2. Okay, it is a twisted.
You take transpose of the affine.
Yes, exactly. Yeah. Because it is a fine picture. So this is. Yeah. So and in fact, if we compute the analog of the Q character, here we get. So the variables have to change to Z for some technical reasons, and then we get Z1 T2 minus 1 Z2 T2. So there are 4 terms. And in fact, their observation is that it's possible to do some association between the elements here. So we have to forget this. So it is the analog of the one that we had for the usual B2. And this term will correspond to this term, this one to this one, and this one to this one. So of course, just an example. So now what we did is to have a general picture of this and to see how to do this systematically. Okay? And so to do this, we defined some, interpolating Qt character. So what is it? What it is? So it lives in some algebra U Qt, which is some Laurent polynomial ring with some variables which depends on 2 parameters. Let's say R, S, and also with some map alpha. Okay, so it's a kind of a double deformation of usual characters. Okay, and then So it's we consider a subring of this, and this is defined by some SL2 condition related to analogs of screening operators, which are related to the definition of double U algebras. Okay. But so this is a subring defined by some SL2 condition. And then theorem, let's say theorem 3, we prove that so this ring, so this is for all quantum affine algebra, so it can be simply laced or non-simply laced. And in the case of non-simply laced, we get this twisted quantum affine algebra. So when t is equal to 1, we get the Grothendieck ring of finite dimensional representation of QG hats. And if I take the other specialization, so the one which motivates the definition, we get representations of the dual quantum group. Okay, so in fact, what is the work? Where is the work here? You may ask. The work is to prove, in fact, the existence of these elements which interpolate between this character, Q character, and twisted character. Okay, you have for all representation an expression here and an expression here, and we prove that it's possible to interpolate this expression in such a way that it lives in this ring here.
This is not at the level of quantum groups, this is at the level of the characters.
Yes, it is not at the level of representations here. But, so I would like to give some precise consequence of this. Okay, because so this result that I told you about this character, which decomposed in the Langlands duality algebra as a sum of characters. So we can formulate this here. So we have a general conjecture, which is the following. So let's take L, finite dimensional representation of this quantum affine algebra. Okay, so let's take key of L, its character, as a UQ of G module. Okay, so it is a representation for the quantum affine algebra, so we can look at the character for the underlying quantum group of finite type. So we can do the transformation that we used for finite type. So we get a character of a UQ of G module. Okay, and now the question, the conjecture is that this is the character of representation of the twisted Langlands duality algebra. Okay, so this is open in general. Okay, so you have a representation of the quantum affine algebra. So we do the transformation for the character. We know that it is a character at the level of the finite type quantum group, but now the question, is it a character of the twisted quantum affine algebra? Okay. And so in general it is open, but by using this interpolating QT character, we can prove this statement for an important family of representation, which are called Kirillov-Reshetikhin modules, and which contains fundamental representations. So in particular, this kind of examples here. So it is theorem 4. That this is true for so Kirillov-Reshetikhin modules. So what are these modules? They are defined by using their Drinfeld polynomials. So they are analogues of a finite dimensional representation whose highest weight is a multiple of a fundamental weight. These are analogues. In type A, they are just evaluation representations of finite dimensional representation of highest weight multiple of fundamental weight, but in general there are no evaluation morphisms, so they are not finite.
Multiple fundamental weights, so it's rectangular diagrams.
Exactly, yes. So why can we prove this? So in general, very few is known about this Q character. There are no analogues of bi-character formulas and so on. But for these Kirillov-Reshetikhin modules, it's possible to prove what is called a special property, which in fact allows to control the Q character of this representation. And then, in fact, so we have this definition of this interpolating Qt character, and we can prove that both specialization have this property. And so as a consequence, we know that the specialization are these Kirillov-Reshetikhin modules on one side and also on the Langlands dual side. And so that this is how we prove this theorem for this. But to prove this conjecture in general, we should have much more information on these finite dimensional representations. Okay, so I will stop.
So any questions?
Maybe we can define this UQT or
In this case, the algebra.
It's too simple.
Yeah.
No. We can define the interpolating quantum group for all Katz modules.
Do you have Serre relations?
Without Serre relations.
You don't have any Serre relations?
No, we cannot interpolate the Serre relation.
But it's difficult to write it down.
No, we have some arguments. So we look.
Just put it on the board.
Could you write down the
You write
definition?
something.
Of this B1? Of course, but you. Okay.
No, in general.
B1
In
is no
general.
good.
Actually, for general cut smooth,
For
it's hard to write.
reanimate.
It's defined by generator and relations.
Can you
So,
do that?
but maybe
Yeah.
you can write down the most interesting relation.
Okay, let's do it.
I think it's just. I think
Okay,
it's
so
just
the
thing
main,
that's strict
so the
to
most
Serre.
interesting relation is this one. Okay.
And these are the diagonal.
And I will explain what it means. Okay, and all this is multiplied by q minus 1 minus 1 qt minus qt. So what does it mean? So these are the positive and negative generators. And this is the analog. So in usual quantum group, you have a relation. So this relation here. Okay? And what we do, in fact, we divide this relation in two relations by using the Casimir element. Okay? Because you know that, so you have x plus x minus x minus x plus, which is equal to some Cartan element here. And so it's possible to write down in the quantum group, the product of the x plus and the x minus, it is equal to the Casimir plus some element which is in the Cartan subalgebra. Okay? And this is exactly what we do here. So this will be the Casimir for the first quantum group, and this is the Casimir for the Langlands dual quantum group. But when we specialize, the Casimir of one quantum group becomes a Cartan element in the Cartan subalgebra. And when we specialize in the other direction, it is the contrary. So this is, but if you, so this element here is very hard to control. So we got it through the representations because we saw that it is exactly what occurs here. But by looking at the action of this and representation of B2, we prove that what should be the Serre relation depends on the representation. So it is a proof that in this picture we cannot write down a universal Serre relation for all representations. So the Serre relations are in the representation but not in the algebra.
We leave them out.
So I hope it's a bit more clear. So this is for B1.
Does it have any other interesting specializations apart from these two?
This is an excellent question. Yes, there should be, but we have not studied. But we should specialize the Q and the T at the same time. You know, but we have not studied this.
But this, if I is not equal, so it is xi, xi. But if I is not equal to j, it is not zero.
It is, yes.
Huh?
They commute. They commute.
It is.
We do not change the relations.
So there are no relations.
Yeah.
So one question one is struck by that maybe the Littleman path model, which only depends on the Weil group, or at least part of it only depends on the Weil group, might be brought in here. I mean
I have some fear because, as I said, it's not compatible with the crystals. This duality.
Well, but the Littleman writes down certain paths.
Yes.
Never mind about whether there are actions on the paths. He writes down certain paths which correspond to the weights. I mean, every path has a weight. Now, he has two things. He has the Weil group, which should be the same for...
It's not changed.
And the other one is an integrality condition, which is changed. So maybe one could just see that some terms will be present in one module and other terms will be present in another module according to the integrality conditions. Maybe.
Yes, maybe, yes. We have not looked at this, but...
In case Cartan matrix is symmetric and R is 1, your
hybrid
quantum group is just neutral?
UQ of G is changed to UQT of G. So it's trivial.
You said in passing that there was no triangular decomposition. So is there any sort of, is there at least any sort of nice inner product that matches a positive against a negative after you specialize into one, or is there?
It should be looked at. If there is one, we try it, but it's not clear. But maybe there is something we have not.
There's no Serre relation.
He doesn't want to.
What's happening in type F4? Do you?
F4?
Yeah.
You can define the algebra.
But you can define the algebra. But this...
You know, as we do not have the Serre relation, what is important is to look node by node what happens. Okay, because you have this relation which will occur for nodes which look like B1,
right,
and the other like SL2 are not really changed, and that's.
But the character decomposition is non-trivial.
No.
What do you mean?
The character decomposition for F4.
Yeah, it's
no, you have a decomposition like for B2.
Because this algebra has one-dimensional representations when Q and T are not specialized.
That's a conjecture. That we at some point we want to develop the representation theory.
Is there a PBW theorem for this algebra?
Hopefully.
Is it flat in Q and T? Or you don't know? For SL2, for example.
It depends in which sense, because we have two parameters.
Flat
yes.
as a Q, say, free module over polynomials in Q and T.
I'm not so sure, but we
because
can discuss
if it was, for example, it's possible. Do you have any reasons to believe that it is flat? Because in principle, it could just blow down to zero in between the points that you're interpolating. So, I mean, what is
No,
the
in fact,
evidence?
we have all straightforward possibility. We have tried. So
but
maybe there is a way to do it, but it's
No.
But do you have any evidence that something like this doesn't happen? That you have 2 points where you get some interesting algebras, and in between it is just zero. Something maybe.
yeah, maybe I don't think so.
Why this algebra doesn't have triangular decomposition? It's not clear from these relations.
No, it's because if you write down the bracket like this, then the terms that you will get do not have some q commutation. So these terms here do not q commute or t commute with the x plus and the x minus. Okay, why do you have a triangular decomposition for quantum field or for Lie algebra? It's because you have the relation between the Cartan subalgebra and the positive part and the negative part. You can change everything. Here you cannot do this so easily. There are some replacements, but it's not as good. So we do not have triangular decomposition, but we can define some Verma modules. It's a bit strange situation.
You can define Verma modules for generic Q and T.
For this algebra, yes.
So that should imply PBW theorem.
Yeah, it depends on the size of the Verma module. It depends what we.
So other questions?
Any more?
Let's thank the speaker again.